Sir Isaac Newton PRSMP/NJUTN/ the 25th of December 1640 to the 20th of March 1727 was an English physicist and mathematician, described in his own day as a natural philosopher who is widely recognized as one of the most influential scientists of all time and as a key figure in the scientific revolution. His book Philosophiæ Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, first published in 1687, laid the foundations for classical mechanics. Newton also made seminal contributions to optics, and shares credit with Gottfried Leibniz for the invention of calculus. Newton's Principia formulated the laws of motion and universal gravitation, which dominated scientists' view of the physical universe for the next 3 centuries. By deriving Kepler's laws of planetary motion from his mathematical description of gravity, and then using the same principles to account for the trajectories of comets, the tides, the precession of the equinoxes, and other phenomena, Newton removed the last doubts about the validity of the heliocentric model of the cosmos. This work also demonstrated that the motion of objects on Earth and of celestial bodies could be described by the same principles. His prediction that the Earth should be shaped as an oblate spheroid was later vindicated by the measurements of Maupertuis, Lacandamine, and others, which helped convince most continental European scientists of the superiority of Newtonian mechanics over the earlier system of Descartes. Newton also built the first practical reflecting telescope and developed a theory of color based on the observation that a prism decomposes white light into the many colors of the visible spectrum. He formulated an empirical law of cooling, studied the speed of sound, and introduced the notion of a Newtonian fluid. In addition to his work on calculus, as a mathematician, Newton contributed to the study of power series, generalized the binomial theorem to non-integer exponents, and developed Newton's method for approximating the roots of a function. Newton was a Fellow of Trinity College and the second Lucasian Professor of Mathematics at the University of Cambridge. He was a devout but unorthodox Christian, and, unusually for a member of the Cambridge faculty of the day, he refused to take holy orders in the Church of England, perhaps because he privately rejected the doctrine of the Trinity. Beyond his work on the mathematical sciences, Newton dedicated much of his time to the study of biblical chronology and alchemy, but most of his work in those areas remained unpublished until long after his death. In his later life, Newton became president of the Royal Society. He also served the British government as warden and master of the Royal Mint. Early life. Isaac Newton was born, according to the Julian calendar in use in England, at the time, on Christmas Day, the 25th of December, 1642, NS the 4th of January, 1643, at Woolsthorpe Manor in Woolsthorpe by Colsterworth, a hamlet in the county of Lincolnshire. He was born 3 months after the death of his father, a prosperous farmer also named Isaac Newton. Born prematurely, he was a small child. His mother Hannah Ayscough reportedly said that he could have fit inside a quart mug, which, depending on the quart measure in use at that time, could have ranged from 2.25 litre, the Winchester quart, in use in England at the time, to 0.95 litre, the US quart, with several possibilities between. When Newton was 3, his mother remarried and went to live with her new husband, the Reverend Barnabas Smith, leaving her son in the care of his maternal grandmother, Marjorie Ayscough. The young Isaac disliked his stepfather and maintained some enmity towards his mother for marrying him, as revealed by this entry in a list of sins committed up to the age of 19, threatening my father and mother Smith to burn them and the house over them. Newton's mother had 3 children from her second marriage. Although it was claimed that he was once engaged, Newton never married. From the age of about 12 until he was 17, Newton was educated at the King's School, Grantham, which taught him Latin, but no mathematics. He was removed from school, and by October 1659, he was to be found at Woolsthorpe by Colsterworth, where his mother, widowed for a second time, attempted to make a farmer of him. He hated farming. Henry Stokes, master at the King's School, persuaded his mother to send him back to school so that he might complete his education. Motivated partly by a desire for revenge against a schoolyard bully, he became the top-rank student, distinguishing himself mainly by building sundials and models of windmills. In June 1661, he was admitted to Trinity College, Cambridge, on the recommendation of his uncle Rev. William Ayscough. He started as a subsizar, paying his way by performing valet's duties, until he was awarded a scholarship in 1664, which guaranteed him 4 more years until he would get his M.A. At that time, the college's teachings were based on those of Aristotle, whom Newton supplemented with modern philosophers such as Descartes, and astronomers such as Galileo and Thomas Street, through whom he learned of Kepler's work. He set down in his notebook a series of questiones about mechanical philosophy, as he found it. In 1665, he discovered the generalized binomial theorem and began to develop a mathematical theory that later became calculus. Soon after Newton had obtained his B.A. degree in August 1665, the university temporarily closed as a precaution against the Great Plague. Although he had been undistinguished as a Cambridge student, Newton's private studies at his home in Woolsthorpe over the subsequent 2 years saw the development of his theories on calculus, optics, and the law of gravitation. In April 1667, he returned to Cambridge, and in October was elected as a Fellow of Trinity. Fellows were required to become ordained priests, although this was not enforced in the Restoration years, and an assertion of conformity to the Church of England was sufficient. However, by 1675 the issue could not be avoided, and by then his unconventional views stood in the way. Nevertheless, Newton managed to avoid it by means of a special permission from Charles II. See Middle Year section, below. His studies had impressed the Lacasian professor, Isaac Barrow, who was more anxious to develop his own religious and administrative potential. He became Master of Trinity 2 years later, and in 1669, Newton succeeded him, only 1 year after he received his M.A. Middle Years. Mathematics. Newton's work has been said to distinctly advance every branch of mathematics then studied. His work on the subject, usually referred to as fluxions or calculus, seen in a manuscript of October 1666, is now published among Newton's mathematical papers. The author of the manuscript De Analysi per Equations Numero Terminorum Infinitus, sent by Isaac Barrow to John Collins in June 1669, was identified by Barrow, in a letter sent to Collins in August of that year, as Newton later became involved in a dispute with Leibniz over priority in the development of calculus, the Leibniz-Newton calculus controversy. Most modern historians believe that Newton and Leibniz developed calculus independently, although with very different notations. Occasionally it has been suggested that Newton published almost nothing about it until 1693, and did not give a full account until 1704, while Leibniz began publishing a full account of his methods in 1684. Leibniz's notation and differential method, nowadays recognized as much more convenient notations, were adopted by continental European mathematicians, and after 1820 or so, also by British mathematicians. Such a suggestion, however, fails to notice the content of calculus which critics of Newton's time and modern times have pointed out in Book 1 of Newton's Principia itself, published 1687, and in its forerunner manuscripts, such as De Motu Corporum Ingirum, on the motion of bodies in orbit of 1684. The Principia is not written in the language of calculus, either as we know it, or as Newton's later notation would write it. His work extensively uses calculus in geometric form based on limiting values of the ratios of vanishing small quantities. In the Principia itself, Newton gave demonstration of this under the name of the method of first and last ratios, and explained why he put his expositions in this form, remarking also that hereby the same thing is performed as by the method of indivisibles. Because of this, the Principia has been called a book dense with the theory and application of the infinitesimal calculus in modern times, and like Wells presque out to ce calcul nearly all of it is of this calculus in Newton's time. His use of methods involving one or more orders of the infinitesimally small is present in his De motu corporum ingerum of 1684. And in his papers on motion, during the 2 decades preceding 1684. Newton had been reluctant to publish his calculus because he feared controversy and criticism. He was close to the Swiss mathematician Nicolas Fauch-D'Illier. In 1691, D'Illier started to write a new version of Newton's Principia and corresponded with Leibniz. In 1693, the relationship between D'Illier and Newton deteriorated, and the book was never completed. Starting in 1699, other members of the Royal Society, of which Newton was a member, accused Leibniz of plagiarism. The dispute then broke out in full force in 1711 when the Royal Society proclaimed in a study that it was Newton who was the true discoverer, and labeled Leibniz a fraud. This study was cast into doubt when it was later found that Newton himself wrote the study's concluding remarks on Leibniz. Thus began the bitter controversy which marred the lives of both Newton and Leibniz until the latter's death in 1716. Newton is generally credited with the generalized binomial theorem, valid for any exponent. He discovered Newton's identities, Newton's method, classified cubic plane curves, polynomials of degree 3 and 2 variables, made substantial contributions to the theory of finite differences, and was the first to use fractional indices and to employ coordinate geometry to derive solutions to Diophantine equations. He approximated partial sums of the harmonic series by logarithms, a precursor to Euler's summation formula, and was the first to use power series with confidence and to revert power series. Newton's work on infinite series was inspired by Simon Stevens' decimals. He was appointed Lucasian Professor of Mathematics in 1669 on Barrow's recommendation. During that time, any fellow of Cambridge or Oxford was required to become an ordained Anglican priest. However, the terms of the Lucasian professorship required that the holder not be active in the church, presumably so as to have more time for science. Newton argued that this should exempt him from the ordination requirement, and Charles II, whose permission was needed, accepted this argument. Thus a conflict between Newton's religious views and Anglican orthodoxy was averted. Optics. In 1666, Newton observed that the spectrum of colors exiting a prism is oblong, even when the light ray entering the prism is circular, which is to say, the prism refracts different colors by different angles. This led him to conclude that color is a property intrinsic to light, a point which had been debated in prior years. Replica of Newton's second reflecting telescope that he presented to the Royal Society in 1672. From 1670 to 1672, Newton lectured on optics. During this period he investigated the refraction of light, demonstrating that the multicolored spectrum produced by a prism could be recomposed into white light by a lens and a second prism. Modern scholarship has revealed that Newton's analysis and resynthesis of white light owes a debt to corpuscular alchemy. He also showed that colored light does not change its properties by separating out a colored beam and shining it on various objects. Newton noted that regardless of whether it was reflected, scattered, or transmitted, it remained the same color. Thus, he observed that color is the result of objects interacting with already colored light rather than objects generating the color themselves. This is known as Newton's theory of color. Illustration of a dispersive prism decomposing white light into the colors of the spectrum, as discovered by Newton. From this work, he concluded that the lens of any refracting telescope would suffer from the dispersion of light into colors, chromatic aberration. As a proof of the concept, he constructed a telescope using a mirror as the objective to bypass that problem. Building the design, the first known functional reflecting telescope, today known as a Newtonian telescope, involved solving the problem of a suitable mirror material and shaping technique. Newton ground his own mirrors out of a custom composition of highly reflective speculum metal, using Newton's rings to judge the quality of the optics for his telescopes. In late 1668 he was able to produce this first reflecting telescope. In 1671, the Royal Society asked for a demonstration of his reflecting telescope. Their interest encouraged him to publish his notes on color, which he later expanded into the work Optics. When Robert Hooke criticized some of Newton's ideas, Newton was so offended that he withdrew from public debate. Newton and Hooke had brief exchanges in 1679-80, when Hooke, appointed to manage the Royal Society's correspondence, opened up a correspondence intended to elicit contributions from Newton to Royal Society transactions, which had the effect of stimulating Newton to work out proof that the elliptical form of planetary orbits would result from a centripetal force inversely proportional to the square of the radius vector. See Newton's law of universal gravitation. History and Demotuco Repo Remengiarum. But the two men remained generally on poor terms until Hooke's death. Facsimile of a 1682 letter from Isaac Newton to Dr. William Briggs, commenting on Briggs' A New Theory of Vision. Newton argued that light is composed of particles or corpuscles, which were refracted by accelerating into a denser medium. He verged on sound like waves to explain the repeated pattern of reflection and transmission by thin films. Optics BK2, props. 12, but still retained his theory of fits that disposed corpuscles to be reflected or transmitted. Props. 13. However, later physicists favored a purely wave-like explanation of light to account for the interference patterns and the general phenomenon of diffraction. Today's quantum mechanics, photons, and the idea of wave-particle duality bear only a minor resemblance to Newton's understanding of light. In his hypothesis of light of 1675, Newton posited the existence of the ether to transmit forces between particles. The contact with the theosophist Henry Moore revived his interest in alchemy. He replaced the ether with occult forces based on Hermetic ideas of attraction and repulsion between particles. John Maynard Keynes, who acquired many of Newton's writings on alchemy, stated that Newton was not the first of the age of reason, he was the last of the magicians. Newton's interest in alchemy cannot be isolated from his contributions to science. This was at a time when there was no clear distinction between alchemy and science. Had he not relied on the occult idea of action at a distance, across a vacuum, he might not have developed his theory of gravity. See also Isaac Newton's occult studies. In 1704, Newton published Optics, in which he expounded his corpuscular theory of light. He considered light to be made up of extremely subtle corpuscles, that ordinary matter was made of grosser corpuscles, and speculated that through a kind of alchemical transmutation are not gross bodies and light convertible into one another, and may not bodies receive much of their activity from the particles of light which enter their composition. Newton also constructed a primitive form of a frictional electrostatic generator, using a glass globe. Optics, 8th query. In an article entitled Newton, Prisms, and the Optics of Tunable Lasers. It is indicated that Newton, in his book Optics, was the first to show a diagram using a prism as a beam expander. In the same book he describes, via diagrams, the use of multiple prism arrays. Some 278 years after Newton's discussion, multiple prism beam expanders became central to the development of narrow-line-width tunable lasers. Also, the use of these prismatic beam expanders led to the multiple prism dispersion theory. Subsequent to Newton, much has been amended. Young and Fresnel combined Newton's particle theory with Huygens wave theory to show that color is the visible manifestation of light's wavelength. Science also slowly came to realize the difference between perception of color and mathematical optics. The German poet, Goethe, could not shake the Newtonian foundation, but one hole Goethe did find in Newton's armor. Newton had committed himself to the doctrine that refraction without color was impossible. He therefore thought that the object glasses of telescopes must forever remain imperfect, achromatism and refraction being incompatible. This inference was proved by Dalland to be wrong. Mechanics and Gravitation. In 1679, Newton returned to his work on celestial mechanics by considering gravitation and its effect on the orbits of planets with reference to Kepler's laws of planetary motion. This followed stimulation by a brief exchange of letters in 1679-80 with Hooke, who had been appointed to manage the Royal Society's correspondence and who opened a correspondence intended to elicit contributions from Newton to Royal Society transactions. Newton's reawakening interest in astronomical matters received further stimulus by the appearance of a comet in the winter of 1680-1681, on which he corresponded with John Flamsteed. After the exchanges with Hooke, Newton worked out proof that the elliptical form of planetary orbits would result from a centripetal force inversely proportional to the square of the radius vector. See Newton's law of universal gravitation history, and De motu corporum ingirum. Newton communicated his results to Edmund Halley and to the Royal Society in De motu corporum ingirum, a tract written on about 9 sheets which was copied into the Royal Society's register book in December 1684. This tract contained the nucleus that Newton developed and expanded to form the Principia. The Principia was published on the 5th of July, 1687, with encouragement and financial help from Edmund Halley. In this work, Newton stated the 3 universal laws of motion that contributed to many advances during the Industrial Revolution which soon followed, and were not to be improved upon for more than 200 years. Many of these advancements continue to be the underpinnings of non-relativistic technologies in the modern world. He used the Latin word gravitas, weight, for the effect that would become known as gravity, and defined the law of universal gravitation. In the same work, Newton presented a calculus-like method of geometrical analysis using first and last ratios, gave the first analytical determination, based on Boyle's law of the speed of sound in air, inferred the oblateness of the spheroidal figure of the Earth, accounted for the precession of the equinoxes as a result of the Moon's gravitational attraction on the Earth's oblateness, initiated the gravitational study of the irregularities in the motion of the Moon, provided a theory for the determination of the orbits of comets, and much more. Newton made clear his heliocentric view of the solar system developed in a somewhat modern way, because already in the mid-1680s he recognized the deviation of the Sun from the center of gravity of the solar system. For Newton, it was not precisely the center of the Sun, or any other body, that could be considered at rest, but rather the common center of gravity of the Earth, the Sun, and all the planets is to be esteemed the center of the world, and the center of gravity either is at rest, or moves uniformly forward in a right line. Newton adopted the at rest alternative in view of common consent, that the center, wherever it was at rest. Newton's postulate of an invisible force able to act over vast distances led to him being criticized for introducing occult agencies into science. Later, in the second edition of the Principia, 1713, Newton firmly rejected such criticisms, in a concluding general scholium, writing that it was enough that the phenomena implied a gravitational attraction, as they did, but they did not so far indicate its cause, and it was both unnecessary and improper to frame hypotheses of things that were not implied by the phenomena. Here Newton used what became his famous expression hypotheses non fingo. With the Principia, Newton became internationally recognized. He acquired a circle of admirers, including the Swiss-born mathematician Nicolas Fauché-Oettler, with whom he formed an intense relationship. This abruptly ended in 1693, and at the same time Newton suffered a nervous breakdown. Classification of cubics. Besides the work of Newton and others on calculus, the first important demonstration of the power of analytic geometry was Newton's classification of cubic curves in the Euclidean plane. In the late 1600s he divided them into 4 types, satisfying different equations, and in 1717 Stirling, probably with Newton's help, proved that every cubic was one of these 4. Newton also claimed that the 4 types could be obtained by plane projection from one of them, and this was proved in 1731. Later life. In the 1690s, Newton wrote a number of religious tracts dealing with the literal and symbolic interpretation of the Bible. A manuscript Newton sent to John Locke, in which he disputed the fidelity of 1 John 5:7 and its fidelity to the original manuscripts of the New Testament, remained unpublished until 1785. Even though a number of authors have claimed that the work might have been an indication that Newton disputed the belief in Trinity, others assure that Newton did question the passage, but never denied Trinity as such. His biographer, scientist Sir David Brewster, who compiled his manuscripts for over 20 years, wrote about the controversy in well-known book Memoirs of the Life, Writings, and Discoveries of Sir Isaac Newton, where he explains that Newton questioned the veracity of those passages, but he never denied the doctrine of Trinity as such. Brewster states that Newton was never known as an Arian during his lifetime. It was first William Whiston, an Arian, who argued that Sir Isaac Newton was so hearty for the Baptists as well as for the Eusebians or Arians that he sometimes suspected these two were the two witnesses in the Revelations, while other like Hopton Haynes, a Mint employee and humanitarian, mentioned to Richard Barron that Newton held the same doctrine as himself. Later works, The Chronology of Ancient Kingdoms amended, 1728, and Observations upon the Prophecies of Daniel and the Apocalypse of St. John, 1733, were published after his death. He also devoted a great deal of time to alchemy, see above. Newton was also a member of the Parliament of England for Cambridge University in 1689-90 and 1701-2, but according to some accounts his only comments were to complain about a cold draught in the chamber and request that the window be closed. Newton moved to London to take up the post of Warden of the Royal Mint in 1696, a position that he had obtained through the patronage of Charles Montague, first Earl of Halifax, then Chancellor of the Exchequer. He took charge of England's great recoining, somewhat treading on the toes of Lord Lucas, Governor of the Tower, and securing the job of Deputy Controller of the temporary Chester branch for Edmund Halley. Newton became perhaps the best-known master of the Mint upon the death of Thomas Neal in 1699, a position Newton held for the last 30 years of his life. These appointments were intended as sinecures, but Newton took them seriously, retiring from his Cambridge duties in 1701, and exercising his power to reform the currency and punish clippers and counterfeiters. As Master of the Mint in 1717, in the law of Queen Anne, Newton moved the pound sterling de facto from the silver standard to the gold standard by setting the bimetallic relationship between gold coins and the silver penny in favor of gold. This caused silver sterling coin to be melted and shipped out of Britain. Newton was made President of the Royal Society in 1703 and an associate of the French Académie des Sciences. In his position at the Royal Society, Newton made an enemy of John Flamsteed, the Astronomer Royal, by prematurely publishing Flamsteed's Historia Celestis Britannica, which Newton had used in his studies. Personal coat of arms of Sir Isaac Newton. In April 1705, Queen Anne knighted Newton during a royal visit to Trinity College, Cambridge. The knighthood is likely to have been motivated by political considerations connected with the parliamentary election in May 1705, rather than any recognition of Newton's scientific work or services as Master of the Mint. Newton was the second scientist to be knighted, after Sir Francis Bacon. Towards the end of his life, Newton took up residence at Cranberry Park, near Winchester, with his niece and her husband, until his death in 1727. His half-niece, Catherine Barton Conduit, served as his hostess in social affairs at his house on Jermyn Street in London. He was her very loving uncle, according to his letter to her, when she was recovering from smallpox. Newton died in his sleep in London, on the 20th of March, 1727, Os the 20th of March, 1726, Ns the 31st of March, 1727, and was buried in Westminster Abbey. Voltaire was present at his funeral and praised the British for honoring a scientist of heretical religious beliefs with burial there. A bachelor, he had divested much of his estate to relatives during his last years and died intestate. After his death, Newton's hair was examined and found to contain mercury, probably resulting from his alchemical pursuits. Mercury poisoning could explain Newton's eccentricity in late life. After death. Fame. The mathematician Joseph Louis Lagrange often said that Newton was the greatest genius who ever lived, and once added that Newton was also the most fortunate, for we cannot find more than once a system of the world to establish. English poet Alexander Pope was moved by Newton's accomplishments to write the famous epitaph. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. Newton himself had been rather more modest of his own achievements, famously writing in a letter to Robert Hooke in February 1676. "If I have seen further, it is by standing on the shoulders of giants." Two writers think that the above quote, written at a time when Newton and Hooke were in dispute over optical discoveries, was an oblique attack on Hooke, said to have been short and hunchbacked, rather than or in addition to a statement of modesty. On the other hand, the widely known proverb about standing on the shoulders of giants, published among others by 17th-century poet George Herbert, a former orator of the University of Cambridge and Fellow of Trinity College, in his Jacula Tridentum, 1651, has as its main point that a dwarf on a giant's shoulder sees farther of the two, and so its effect, as an analogy, would place Newton himself rather than Hooke as the dwarf. In a later memoir, Newton wrote, "I do not know what time may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble, or a prettier shell, than ordinary, whilst the great ocean of truth lay all undiscovered before me." In 1816 a tooth said to have belonged to Isaac Newton was sold for 730 us, 633, in London, to an aristocrat who passed to have it set in a ring. The Guinness World Records 2002 classified it as the most valuable tooth, which would value approximately 25,000 us 5,700 in late 2001's terms. Who has bought it, and to whom it currently pertains, are mysteries. Albert Einstein kept a picture of Newton on his study wall alongside ones of Michael Faraday and James Clerk Maxwell. Newton remains influential to today's scientists, as demonstrated by a 2005 survey of members of Britain's Royal Society, formerly headed by Newton, asking who had the greater effect on the history of science, Newton or Einstein. Royal Society's scientists deemed Newton to have made the greater overall contribution. In 1999, an opinion poll of 100 of today's leading physicists voted Einstein the greatest physicist ever, with Newton the runner-up, while a parallel survey of rank-and-file physicists by the site PhysicsWeb gave the top spot to Newton. Commemorations. Newton's statue on display at the Oxford University Museum of Natural History. Newton's monument, 1731, can be seen in Westminster Abbey, at the north of the entrance to the choir against the choir screen, near his tomb. It was executed by the sculptor Michael Rysbrack, 1694-1770, in white and grey marble with design by the architect William Kent. The monument features a figure of Newton reclining on top of a sarcophagus, his right elbow resting on several of his great books, and his left hand pointing to a scroll with a mathematical design. Above him is a pyramid, and a celestial globe showing the signs of the zodiac, and the path of the comet of 1680. A relief panel depicts putty using instruments such as a telescope and prism. The Latin inscription on the base translates as, "Here is buried Isaac Newton, knight, who by a strength of mind almost divine, and mathematical principles peculiarly his own, explored the course and figures of the planets, the paths of comets, the tides of the sea, the dissimilarities in rays of light, and, what no other scholar has previously imagined, the properties of the colors thus produced." Diligent, sagacious and faithful in his expositions of nature, antiquity, and the Holy Scriptures, he vindicated by his philosophy the majesty of God mighty and good, and expressed the simplicity of the gospel in his manners. mortals rejoice that there has existed such and so great an ornament of the human race. He was born on the 25th of December, 1642, and died on the 20th of March, 1726/7. Translation from G. L. Smith, The Monuments and Genii of St. Paul's Cathedral, and of Westminster Abbey, 1826, I. 703-4. From 1978 until 1988, an image of Newton designed by Harry Ecclestone appeared on Series D1 banknotes issued by the Bank of England, the last one notes to be issued by the Bank of England. Newton was shown on the reverse of the notes holding a book, and accompanied by a telescope, a prism, and a map of the solar system. Edoardo Palazzi's Newton, after William Blake, 1995, outside the British Library. A statue of Isaac Newton, looking at an apple at his feet, can be seen at the Oxford University Museum of Natural History. A large bronze statue, Newton, after William Blake, by Edoardo Palazzi, dated 1995, and inspired by Blake's etching, dominates the piazza of the British Library in London. In popular culture. Personal life. Newton never married. The French writer and philosopher Voltaire, who was in London at the time of Newton's funeral, said that he was never sensible to any passion, was not subject to the common frailties of mankind, nor had any commerce with women, a circumstance which was assured me by the physician and surgeon who attended him in his last moments. The widespread belief that he died a virgin has been commented on by writers including mathematician Charles Hutton, 87, economist John Maynard Keynes, and physicist Carl Sagan. Newton did have a close friendship with the Swiss mathematician Nicolas Fauchet-Delire, whom he met in London, around 1690. Their friendship came to an unexplained end in 1693. Some of their correspondence has survived. Newton was one of many people who lost heavily when the South Sea Company collapsed. Their most significant trade was slaves, and according to his niece, he lost around 20,000. Religious views. Newton's tomb in Westminster Abbey. Although born into an Anglican family, by his 30s Newton held a Christian faith that, had it been made public, would not have been considered orthodox by mainstream Christianity. In recent times he has been described as a heretic. When Newton received his M.A. and became a Fellow of the College of the Holy and Undivided Trinity, in 1667, he made the commitment that I will either set theology as the object of my studies, and will take holy orders when the time prescribed by these statutes 7 years arrives, or I will resign from the college. Up till this point he had not thought much about religion, and had twice signed his agreement to the 39 Articles, the basis of Church of England doctrine. By 1672 he had started to record his theological researches in notebooks which he showed to no one and which have only recently been examined. They demonstrate an extensive knowledge of early church writings, and show that in the conflict between Athanasius and Arius which defined the creed, he took the side of Arius, the loser, who rejected the conventional view of the Trinity. Newton recognized Christ as a divine mediator between God and man, who was subordinate to the Father, who created him. He was especially interested in prophecy, but for him, the great apostasy was Trinitarianism. Newton tried unsuccessfully to obtain one of the 2 fellowships that exempted the holder from the ordination requirement. At the last moment in 1675 he received a dispensation from the government that excused him and all future holders of the Lucasian chair. In Newton's eyes, worshipping Christ as God was idolatry, to him the fundamental sin. Historian Stephen D. Snowblin says of Newton, Isaac Newton was a heretic. But he never made a public declaration of his private faith which the orthodox would have deemed extremely radical. He hid his faith so well that scholars are still unraveling his personal beliefs. Snowblin concludes that Newton was at least a Socinian sympathizer. He owned and had thoroughly read at least 8 Socinian books, possibly an Arian, and almost certainly an anti-Trinitarian. In a minority view, T.C. Fitz-Enmeyer argues that Newton held the Eastern Orthodox view on the Trinity. However, this type of view has lost support of late with the availability of Newton's theological papers, and now most scholars identify Newton as an anti-Trinitarian monotheist. Although the laws of motion and universal gravitation became Newton's best-known discoveries, he warned against using them to view the universe as a mere machine, as if akin to a great clock. He said, "Gravity explains the motions of the planets, but it cannot explain who set the planets in motion. God governs all things and knows all that is, or can be done." Along with his scientific fame, Newton's studies of the Bible and of the early church fathers were also noteworthy. Newton wrote works on textual criticism, most notably an historical account of two notable corruptions of Scripture. He placed the crucifixion of Jesus Christ at the 3rd of April, at 33, which agrees with one traditionally accepted date. He also tried unsuccessfully to find hidden messages within the Bible. He believed in a rationally immanent world, but he rejected the hylozoism implicit in Leibniz and Baruch Spinoza. The ordered and dynamically informed universe could be understood, and must be understood, by an active reason. In his correspondence, Newton claimed that in writing the Principia I had an eye upon such principles as might work with considering men for the belief of a deity. He saw evidence of design in the system of the world. Such a wonderful uniformity in the planetary system must be allowed the effect of choice. But Newton insisted that divine intervention would eventually be required to reform the system, due to the slow growth of instabilities. For this, Leibniz lampooned him. "God Almighty wants to wind up his watch from time to time, otherwise it would cease to move." He had not, it seems, sufficient foresight to make it a perpetual motion. Newton's position was vigorously defended by his follower Samuel Clerk, in a famous correspondence. A century later, Pierre-Simon Laplace's work Celestial Mechanics had a natural explanation for why the planet orbits don't require periodic divine intervention. Effect on religious thought. Newton and Robert Boyle's approach to the mechanical philosophy was promoted by rationalist pamphleteers as a viable alternative to the pantheists and enthusiasts, and was accepted hesitantly by orthodox preachers as well as dissident preachers, like the latitudinarians. The clarity and simplicity of science was seen as a way to combat the emotional and metaphysical superlatives of both superstitious enthusiasm and the threat of atheism, and at the same time, the second wave of Englishites used Newton's discoveries to demonstrate the possibility of a natural religion. Newton, by William Blake. Here, Newton is depicted critically as a divine geometer. This copy of the work is currently held by the Tate Collection. The attacks made against pre-Enlightenment magical thinking and the mystical elements of Christianity were given their foundation with Boyle's mechanical conception of the universe. Newton gave Boyle's ideas their completion through mathematical proofs and, perhaps more importantly, was very successful in popularizing them. Newton refashioned the world governed by an interventionist God into a world crafted by a God that designs along rational and universal principles. These principles were available for all people to discover, allowed people to pursue their own aims fruitfully in this life, not the next, and to perfect themselves with their own rational powers. Newton saw God as the master creator, whose existence could not be denied in the face of the grandeur of all creation. His spokesman, Clerk, rejected Leibniz's theodicy, which cleared God from the responsibility for origine du mal by making God removed from participation in his creation, since, as Clerk pointed out, such a deity would be a king in name only, and but one step away from atheism. But the unforeseen theological consequence of the success of Newton's system over the next century was to reinforce the disposition advocated by Leibniz. The understanding of the world was now brought down to the level of simple human reason, and humans, as Odo Marquard argued, became responsible for the correction and elimination of evil. End of the world. In a manuscript he wrote in 1704, in which he describes his attempts to extract scientific information from the Bible, he estimated that the world would end no earlier than 2060. In predicting this, he said, This I mention not to assert when the time of the end shall be, but to put a stop to the rash conjectures of fanciful men, who are frequently predicting the time of the end, and by doing so bring the sacred prophecies into discredit as often as their predictions fail. Alchemy. Speculative fiction author Fritz Leiber said of Newton, "Everyone knows Newton as the great scientist. Few remember that he spent half his life muddling with alchemy, looking for the philosopher's stone. That was the pebble by the seashore he really wanted to find." Enlightenment philosophers. Enlightenment philosophers chose a short history of scientific predecessors. Galileo, Boyle, and Newton principally as the guides and guarantors of their applications of the singular concept of nature and natural law to every physical and social field of the day. In this respect, the lessons of history and the social structures built upon it could be discarded. It was Newton's conception of the universe based upon natural and rationally understandable laws that became one of the seeds for Enlightenment ideology. Locke and Voltaire applied concepts of natural law to political systems advocating intrinsic rights, the physiocrats, and Adam Smith applied natural conceptions of psychology and self-interest to economic systems, and sociologists criticized the current social order for trying to fit history into natural models of progress. Mombado and Samuel Clarke resisted elements of Newton's work, but eventually rationalized it to conform with their strong religious views of nature. Royal Mint. As warden, and afterwards master, of the Royal Mint, Newton estimated that 20% of the coins taken in during the Great Recoinage of 1696 were counterfeit. Counterfeiting was high treason, punishable by the felons being hanged, drawn and quartered. Despite this, convicting the most flagrant criminals could be extremely difficult. However, Newton proved to be equal to the task. Disguised as a habitué of bars and taverns, he gathered much of that evidence himself. For all the barriers placed to prosecution, and separating the branches of government, English law still had ancient and formidable customs of authority. Newton had himself made a justice of the peace in all the home counties. There is a draft of a letter regarding this matter stuck into Newton's personal first edition of his Philosophiæ Naturalis Principia Mathematica, which he must have been amending at the time. Then he conducted more than 100 cross-examinations of witnesses, informers, and suspects between June 1698 and Christmas 1699. Newton successfully prosecuted 28 coiners. One of Newton's cases as the king's attorney was against William Chaloner. Chaloner's schemes included setting up phony conspiracies of Catholics, and interning in the hapless conspirators, whom he had entrapped. Chaloner made himself rich enough to posture as a gentleman. Petitioning Parliament, Chaloner accused the Mint of providing tools to counterfeiters, a charge also made by others. He proposed that he be allowed to inspect the Mint's processes in order to improve them. He petitioned Parliament to adopt his plans for a coinage that could not be counterfeited, while at the same time striking false coins. Newton put Chaloner on trial for counterfeiting, and had him sent to Newgate Prison in September 1697. But Chaloner had friends in high places, who helped him secure an acquittal and his release. Newton put him on trial a second time, with conclusive evidence. Chaloner was convicted of high treason, and hanged, drawn and quartered on the 23rd of March, 1699, at Tyburn Gallows. As a result of a report written by Newton on the 21st of September, 1717 to the Lords Commissioners of His Majesty's Treasury, the bimetallic relationship between gold coins and silver coins was changed by royal proclamation on the 22nd of December, 1717, forbidding the exchange of gold guineas for more than 21 silver shillings. This inadvertently resulted in a silver shortage, as silver coins were used to pay for imports, while exports were paid for in gold, effectively moving Britain from the silver standard to its first gold standard. It is a matter of debate as whether he intended to do this or not. It has been argued that Newton conceived of his work at the Mint as a continuation of his alchemical work. Newton's first law, also known as the law of inertia, states that an object at rest tends to stay at rest, and that an object in uniform motion tends to stay in uniform motion, unless acted upon by an external force. The meaning of this law is the existence of reference frames, called inertial frames, where objects not acted upon by forces move in uniform motion. In particular, they may be at rest. Newton's second law states that an applied force on an object equals the rate of change of its momentum with time. Mathematically, this is expressed as, since the law applies only to systems of constant mass, can be brought out of the derivative operator. By substitution using the definition of acceleration, the equation can be written in the iconic form. The first and second laws represent a break with the physics of Aristotle, in which it was believed that a force was necessary in order to maintain motion. They state that a force is only needed in order to change an object's state of motion. The unit of force is the Newton, named in Newton's honor. Newton's third law states that for every action there is an equal and opposite reaction. This means that any force exerted onto an object has a counterpart force that is exerted in the opposite direction back onto the first object. A common example is of two ice skaters pushing against each other and sliding apart in opposite directions. Another example is the recoil of a firearm, in which the force propelling the bullet is exerted equally back onto the gun and is felt by the shooter. Since the objects in question do not necessarily have the same mass, the resulting acceleration of the two objects can be different, as in the case of firearm recoil. Unlike Aristotle's, Newton's physics meant to be universal. For example, the second law applies both to a planet and to a falling stone. The vector nature of the second law addresses the geometrical relationship between the direction of the force and the manner in which the object's momentum changes. Before Newton, it had typically been assumed that a planet orbiting the Sun would need a forward force to keep it moving. Newton showed instead that all that was needed was an inward attraction from the Sun. Even many decades after the publication of the Principia, this counterintuitive idea was not universally accepted, and many scientists preferred Descartes' theory of vortices. Apple incident. Reputed descendants of Newton's apple tree, from top to bottom, at Trinity College, Cambridge, the Cambridge University Botanic Garden, and the Instituto Bolsero Library Garden. Newton himself often told the story that he was inspired to formulate his theory of gravitation by watching the fall of an apple from a tree. Although it has been said that the apple story is a myth, and that he did not arrive at his theory of gravity in any single moment, acquaintances of Newton, such as William Stukeley, whose manuscript account of 1752 has been made available by the Royal Society, do in fact confirm the incident, though not the cartoon version, that the apple actually hit Newton's head. Stukeley recorded in his memoirs of Sir Isaac Newton's life a conversation with Newton in Kensington, on the 15th of April, 1726. We went into the garden, and drank tea, under the shade of some apple trees, only he, and myself. Amidst other discourse, he told me, he was just in the same situation, as when formerly, the notion of gravitation came into his mind. Why should that apple always descend perpendicularly to the ground, thought he to himself, occasion it by the fall of an apple, as he sat in a contemplative mood? Why should it not go sideways, or upwards, but constantly to the earth's center? Assuredly, the reason is, that the earth draws it. There must be a drawing power in matter, and the sum of the drawing power in the matter of the earth must be in the earth's center, not in any side of the earth. Therefore does this apple fall perpendicularly, or toward the center. If matter thus draws matter, it must be in proportion of its quantity. Therefore the apple draws the earth, as well as the earth draws the apple. John Conduit, Newton's assistant at the Royal Mint and husband of Newton's niece, also described the event, when he wrote about Newton's life. In the year 1666 he retired again from Cambridge, to his mother in Lincolnshire. Whilst he was pensively meandering in a garden, it came into his thought that the power of gravity, which brought an apple from a tree to the ground, was not limited to a certain distance from Earth, but that this power must extend much further than was usually thought. Why not as high as the moon, said he to himself, and if so, that must influence her motion, and perhaps retain her in her orbit, whereupon he fell a calculating what would be the effect of that supposition. In similar terms, Voltaire wrote in his essay on epic poetry, 1727, Sir Isaac Newton, walking in his gardens, had the first thought of his system of gravitation, upon seeing an apple falling from a tree. It is known from his notebooks that Newton was grappling in the late 1660s with the idea that terrestrial gravity extends, in an inverse square proportion, to the moon. However, it took him 2 decades to develop the full-fledged theory. The question was not whether gravity existed, but whether it extended so far from Earth that it could also be the force holding the moon to its orbit. Newton showed that if the force decreased as the inverse square of the distance, one could indeed calculate the moon's orbital period and get good agreement. He guessed the same force was responsible for other orbital motions and hence named it universal gravitation. Various trees are claimed to be the apple tree which Newton describes. The King's School, Grantham, claims that the tree was purchased by the school, uprooted and transported to the headmaster's garden some years later. The staff of the now National Trust-owned Woolsthorpe Manor dispute this, and claim that a tree present in their gardens is the one described by Newton. A descendant of the original tree can be seen growing outside the main gate of Trinity College, Cambridge, below the room Newton lived in when he studied there. The National Fruit Collection at Brogdale can supply graphs from their tree, which appears identical to Flower of Kent, a coarse-fleshed cooking variety,